Hello everyone and welcome back to the series of digital logic design, and today we will study the map method. Now we will study gate level minimization. Gate level minimization is a design task of finding an optimal gate level implementation of a Boolean function describing a digital circuit. For example, you have tasked to design a system and you end up with the equation which represents working of the system. Now, as a design engineer, you have to optimize the design so that it must consume minimum space and have minimum time delay for input to reach the output. And this is achieved using gate level minimization and will make the circuit implementation easier. When a given logic or the Boolean function have more than a few inputs, it becomes difficult or hectic to simplify the given Boolean expression. For example, if you have a system which consists of 4 or more than 5 variables, then it is not easy to simplify the given equation using algebraic manipulation or any other method. But fortunately, in this case, computer-based logic synthesis tool can minimize a large set of Boolean equations effectively and quickly. Now we know that the complexity of a digital logic system is directly related to complexity of an algebraic expression through which the desired function is implemented. And we also know that the truth table representation of an algebraic expression or the Boolean function is unique. But when the same function is expressed algebraically, then it may appear in different equivalent forms. So we can say that if we have a complex function and if we have a simplified function, and corresponding to both, the truth table is unique, so the implementation of a simplified circuit is more easier and will occupy less space compared to the complex one. So we prefer gate level minimization for an optimal gate design. Now, a Boolean expression may be simplified using the algebraic rule, but this procedure of minimization seems awkward because it lacks the specific rules to predict in each succeeding step in the manipulative process. Like if you have a Boolean expression which you are going to simplify, then you can apply a series of steps, but which rule is to be preferred or which rule is to be applied first is a bit tough to decide every time. The solution or the alternative to the use of Boolean expression rules for simplification is the map method. The map method gives a simple, straightforward procedure for minimizing a Boolean function, and this method may be regarded as a pictorial form of the truth table because this method uses the truth table or the canonical form of a Boolean expression for the simplification purpose. And this method is known as Karnaugh map or the kmap. The kmap is made up of squares with each square representing one minterm of the function which has to be minimized. Now we know that any Boolean function can be expressed as the sum of minterms. So the given Boolean function is recognized graphically in the map from the area which is being covered by those squares whose minterms are included in the function. In fact, the map represents the visual diagram of all the possible ways that a function may be expressed in the standard form. Now by selecting various patterns of minterms on the map, the user can derive an alternative algebraic expression for the same function. Then among those patterns, a user can select the simplest one. The simplified expression produced by a map are always in the one of the two standard form. The first one is sum of product or the second one is product of sum. Now here it is assumed that the simplest algebraic expression is an algebraic expression with minimum number of terms and with the smallest possible number of literals in each term. And this simplified expression produces a circuit diagram with minimum number of gates and minimum number of inputs to the gate. As we said that the simplest Boolean expression will have minimum number of terms, and corresponding to these minimum number of terms, will result in minimum number of gates, and the second point was the minimum number of literals in each term. So corresponding to this, we will have minimum number of input to each gate. Like we said that a user can select various patterns of squares and then he has to identify the simplest equation among those. This means that the algebraic representation of a Boolean function is not unique. It is sometimes possible to find two or more expressions that satisfy the minimization criteria. In that case, either solution is satisfactory.
Thanks for watching the video and stay connected for more interesting videos.